All right, we are going to finish chapter 8 by talking about molecular orbital theory. And molecular orbital theory comes to us because of some experimental results, which is why I have the lab in my background here. And when we take a look at a property, diamagnetic and paramagnetic, now we've seen this before, and a molecule or atom is diamagnetic if all of the electrons are paired. In other words, if in every orbital I have both one that is up and one that is down, I have opposite spins all present. If I have an orbital that has an unpaired of electron, I have something that is paramagnetic. For example, nitrogen has a 2s and a 2p that we see here. But we also expect nitrogen to be diamagnetic if I have N2. And both of these match what we expect. However, when we start looking at oxygen, we expect oxygen. Oxygen is going to have almost the same thing. It's also going to be paramagnetic as an atom. But when we see the oxygen molecule, 1, 2, 3, 4, 1, 2, 3, 4, we expect it to be diamagnetic, everything paired up, which means if it's run through a magnetic field, it should be slightly repelled, but that's not what we see. We actually see if liquid oxygen is put through a magnetic field, it is attracted by that magnetic field, indicating that it is paramagnetic. That doesn't match our valence bond theory prediction. So we're going to have to come up with a new theory. Actually, somebody's already done that for us. And this is just a cool picture of a Gauss balance, which can actually measure the number of unpaired electrons in a particular sample, okay? In order to understand the molecular orbital theory, we need to remember that orbitals are wave functions. And if we combine waves where the crests and troughs overlap, we get constructive interference. We have a greater intensity. And if they're out of phase or opposite with each other, I get destructive interference and get no intensity there. So let's take two s orbitals. And if I combine two s orbitals, well, one of the rules for molecular orbital theory is the number of molecular orbitals is equal to the number of atomic orbitals that are combined. So if I combine these two atomic orbitals, I will get two molecular orbitals. Now, if I have constructive interference, I have what is called a bonding molecular orbital. And if I have destructive interference, I end up with an anti-bonding molecular orbital. So I represent the anti-bonding with an asterisk. And these are represented as sigmas, okay? I can also get sigma bonds from p orbitals. Now, if p orbitals are along the same axis, then I can have an overlap that is going to give me a bonding molecular orbital, and overlap that gives me an anti-bonding molecular orbital. Now, this is if they're in the same axis. If the axes are parallel, I'm going to end up with pi bonds. Now, again, I can have the constructive interference giving me the pi bonding molecular orbital and the pi anti-bonding molecular orbital. Walter Kohn was one of the people who developed molecular orbital theory. And what's nice about it is it allows us to give calculations. So by knowing the structure, just the way which atoms are involved and which molecules are put together, we can calculate the three-dimensional structure of something like HIV protease. And this is like thousands of atoms combined together. And we can predict precisely where the atoms are going to end up. This is all because of molecular orbital theory. Now, don't worry, the math that's involved in that is significantly higher than differential equations, and we need to use computers to be able to do the calculations in our lifetimes. So because of this, this is not something that we're going to actually do in Gen Chem 1. It is something that you need to know can be done. We also need to understand bond order. Now, bond order is taking the number of bonding electrons minus anti-bonding electrons divided by 2. That is for molecular orbital theory. Now, for our valence bond theory, it's very simple. A single bond is a bond order of 1. A double bond is a bond order of 2. Now, I can have fractional bond orders. For example, if I have the sulfur dioxide molecule, and that's supposed to be an S there. Notice that I have one, oh, I did this wrong. All right, so I'm supposed to have this flipped. So let's see if I can do this again. I've got 1, 2, 3 bonds here and 2 resonance structures. 3 bonds over 2 resonance structures gives me a bond order of 1.5. So I can get fractional bond orders even through the valence bond theory. Okay. Now, molecular orbital theory combines the orbitals. Now, just like we could do orbital diagrams for atoms, we can do orbital diagrams for molecules. And when I combine the orbitals, I'm going to get, for example, with hydrogen, I get the 1s and the 1s anti-bonding orbitals. And I follow the same principle, the Aufbau principle and Hund's rule. Fill from the bottom up and 1 electron in each if they're degenerate. In this case, I get a bond order of 2 bonding electrons minus 0 bonding electrons so 2 minus 0 divided by 2. This gives me a bond order of 1. This is what we would expect for hydrogen. And I know you're thinking He2. That's funny, but it's really not funny because our bond order, I have 2 bonding minus 2 anti-bonding, which is 0. 0 by 2 is 0. So He2 is not going to form. Not funny. Okay. We move on to the second period, and the first period electrons are going to give us a total bonding contribution of 0. When we take a look at the second period, or the valence electrons here, we see that we have the possibility of Be2 plus having 2 bonding and 1 anti-bonding electron, giving us a bond order of 1/2. Okay. Now, I can do this. This is a set of diagrams for the second period elements. And let's just say, for example, I have nitrogen. Now, with the 2 nitrogen atoms, I have a total of 5 valence electrons from each nitrogen. I know nitrogen has 7 valence electrons, but there are only 5 valence electrons, 7 total, 2 are in the 1s. So if I fill 10 up, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have the 2 anti-bonding. I have 8 bonding. 8 minus 2 is 6. 6 divided by 2 is 3. This gives me a bond order of 3, the expected triple bond that I see in nitrogen. For oxygen, I expect to see a double bond. So let's fill up. Oxygen is going to have 12. 1, 2, 3, 4. This is a little tricky here because it's not very big. 5, 6, 7, 8, 9, 10, 11, 12. Okay. I have 2, 4 antibonding and 2, 4, 6, 8 bonding. 8 minus 4 is 4. 4 divided by 2 is 2. And what do you know? Here I have unpaired electrons. So O2 is actually paramagnetic, just as experiment shows us. So we can see that in the previous diagram, this sigma 2px kind of decreases in energy, even though the pi's are almost constant the whole way through. And what happens is we start seeing mixing of electrons, and you don't need to worry about memorizing that. You won't be expected to memorize the diagrams, just be able to use them, okay? So here we see a flip of the sigma p orbital going higher in energy than the pi 2p's, okay? Now, when we start looking at this, a lot of the molecular orbitals in solids are so close together that they're described as bands, okay? And if there is a gap between the valence and the conduction band, okay, so between the filled band and the unfilled band, if there's a big gap there, we call that an insulator because electrons are not going to jump from here to here. If it's a small gap, that band gap is small enough that some electrons can jump that gap, we call it a semiconductor. And if it's very close together, we call this a conductor, okay? Here is, again, a little bit nicer prediction of O2, showing the two unpaired electrons that we see up here. And this is our molecular orbital theory. At this point, your exam is going to be over chapters 6, 7, and 8. And again, you do not have to memorize the orbital diagrams. You just need to be able to use them. All right.